Chapter 5. We are now in 5.2. And this chapter 5 is about using trigonometric identities. In 5.1, we looked at sort of fundamental identities like sine squared x plus cosine squared x equals 1, being the most fundamental identity that we use and reuse a bunch of times. So in 5, and we looked at some other fundamental identities. So in 5.2, we are going to begin to take all of those fundamental identities that we worked with, and we're going to think about how to expand those to possibly verify new identities based on the ones that we've already looked at. And so the main things we're going to focus on are just strategies for looking at possible identities in trig and trying to verify that they're valid or not. And a couple of the strategies specific we're going to look at are verifying identities by working with one side. Again, an identity, to identify, we're going to have an equality in there. And when you're working with one side, the idea is you started with, something equals something, and you just try to change one side to make it look like the other side so that you can confirm they're equal. And then also verifying identities by working with both sides, where maybe you do the same thing to both sides like you might do when you're solving an equation, as another possible strategy. So anyway, so this is an overview of the three main things that we want to consider in section 2 of chapter 5. So let's look at this for a second. Like our primary identity we have, for example, where we have sine squared theta plus cosine squared theta is equal to 1. So this is one of the identities that we have that we can work with. And so we also have an identity that tan squared theta plus 1 is equal to secant squared theta. So these are both given to us in some of our fundamental identities. But let's say that we have this one. Let's say we were given the first one and we were asked to verify the second one. So this is the kind of thing that we're talking about doing in 5.2. When they say verifying an identity, you're going to be given a goal of figuring out if this statement or equation is true, to verify it. And somehow you want to do that using ones that you already know, that were given in the past. This is the idea of this section in a simple example, and then we can look at all the different examples that they give us and have us practice. And so if that was the goal, we'll say that I have the identity on the top that's given and I want to verify the one on the bottom, then in this case, for example, I could show that I could do that by using the second or the last thing they referred to here, verifying identities by working with both sides. What I could do with the identity above is I could divide both sides by cosine theta. If I divide the left side by cosine, I should have said squared, cosine squared theta. If I divide both sides by cosine squared theta, then what you'll see on the right side is that 1 divided by cosine squared theta is secant squared theta. That was one of our reciprocal identities. And on the left side, when I have these two things that are divided by cosine squared theta, sine squared theta divided by cosine squared theta gives me tan squared theta. And cosine squared theta divided by cosine squared theta gives me 1. And so if I take the first identity there, that's one of the given ones we have to work with, and I divide both sides of that equation by cosine squared theta, I can then get the second equation that I'm supposed to verify, and that's how I verify it, by doing the same thing to both sides of the first identity allowed me to get the identity that I was supposed to verify. So this is sort of the idea of the kinds of stuff we're going to be doing in 5.2 with a real simple example before we look at the ones that they give us. All right, so let's look at what they offer us to begin down this road. Hints for verifying identities. Whenever you see either side of a fundamental identity, the other side should come to mind. So the simplest example of that is if you see cosine squared theta plus sine squared theta, you want to say, oh, that's just 1, because in the fundamental identity, that's equal to 1. Or if you see, as we just looked at, tan squared theta plus 1, well, then you can say, oh, that's just the same as secant squared theta. So it's a little odd for them to say the other side should come to mind, because that's basically saying that you just think of the other side. And of course, that's not normally naturally going to occur until you've worked with these for a while. So for what they're recommending here to work well for you, initially it won't just pop into your mind, but what you'll do is you'll look over the identities that you've been given. You'll look over the fundamental identities to see if something on one side of those is in the problem that you're looking at. And then you'll think, oh, there's cosine squared theta plus sine squared theta. I can replace that with a 1. And then after you've done that a few times, then maybe it'll just come to mind. But to sort of say, well, this should just come to mind, that's not going to start out that way. Initially, you'll just keep referring to the fundamental identities until you start to recognize what they tell you and how to apply those to problems. And then you won't have to look them up as much. So it then has also tried to rewrite the more complicated side of the equation so that it is identical to the simpler side. This is a very good strategy, because what we're going to be doing, as I mentioned in 5.1, is going to be very algebraic. There's going to be a lot of algebra, multiplying both sides, adding and subtracting both sides, simplifying fractions, things like that. And most of the algebra training that students have had have been to simplify things that are complicated, like combining like terms, canceling common factors in fractions, things like that. And so most of the algebra training that you've had in the past will serve you well if you're trying to take more complicated things and simplifying them. And so if you have an identity you're supposed to verify where one side is more complicated and the other side is simpler, naturally, it will work better for most students to try to simplify and rewrite the more complicated side and see if it comes out like the simpler side, and then you verify that the two sides are equal. So this is a very good recommendation that they have here, but you have to kind of think about what they're saying there as well. And again, you can't just read these and then apply them all immediately, but by showing you up front the ideas of the strategies that we're going to try to learn by doing examples, hopefully then as you start working with examples and you see some done for you, you can understand how they did it and how they knew to do what they did. More hints. It's sometimes helpful to express all trigonometric functions in the equations in terms of sine and cosine, and then simplify the result. So I actually mentioned this also in 5.1. And I said it's often going to be the case that you're just going to convert everything to sine and cosine and then simplify if you get fractions or clear fractions or do algebra stuff to simplify. And then maybe you'll be able to end up with the results you're looking for. None of these are going to be a guaranteed strategy, and each problem might require something a little different. But these main hints that they're giving here are kind of the ideas of how you approach most of these identity problems and the strategies that you'll use. So this is also a very good one. Next, it says, usually any factoring or indicated algebraic operations should be performed. And that's definitely how algebra is really going to be put to a lot of use in all of these problems in chapter 5. So they have an example here. Factoring was a big skill taught in algebra 1 and algebra 2, but typically for polynomials. So factoring, when there's all these trig functions in there, takes some getting used to. So in this example, they have the expression sine squared x plus 2 sine x plus 1 can be factored into sine x plus 1 squared. So how would you see that or recognize that? Maybe some of you already do. That would be great. But what they're trying to show, for example, here is that when they say sine squared x, that means you have the sine x function squared. And then you also have 2 times the sine x function plus a 1 added. So you can see it or think of it that way. And then you can compare this by thinking about, well, what if this sine x function was just a variable like u? In algebra, we would refer to this as a u substitution. So if you imagine that even though sine x is more complicated than just u, but since it occurs in more than one place, and we're always talking about trig functions like sine x, just imagine that when they say sine x is squared and it's 2 times sine x, that what if you just replace that with a u, then this would be u squared plus 2u plus 1. And if you imagine or think or make that substitution, then all of a sudden it looks like factoring that you did in algebra. Then you may be able to recall that this was called a trinomial and that we practiced factoring trinomials. And then u squared is achieved by doing u times u. 1 is achieved by multiplying 1 times 1. And then you could confirm that if you FOILed this out, u times u is u squared, 1 times 1 is 1, and you have u plus u to give you 2u in the middle, so that this is a proper factoring. And since the two binomials are exactly the same, you could rewrite that as u plus 1. Whoops, that's doing weird things. I'm not sure how to get rid of that. Let's see here, back. Somehow I zoomed in. I didn't even know I could do that. I'm not sure how to get rid of it. Like that, there we go. U plus 1 squared. And so if you, by substituting in for u or thinking of the sine x function just as a u, if you then could more easily see this as a polynomial of the kind that you factored a lot in algebra, then maybe the factoring gets a little easy. But you do in the end want to remember that u is actually just been a replacement for sine x. So if I put that back in, then the factoring becomes u is now sine x plus 1, and that all of that is squared, and that's what they had here. So they don't even tell you to look at it that way, and you don't have to look at it that way. But that's the idea of what's going on when they say this expression can be factored like that. They didn't show it being done. They didn't make it look like a polynomial, which is the kind of stuff you factored before. And so sometimes some of these details will help you kind of see what they're talking about. So if you have something like this, well, you want to be able to recognize that it could be factored into something like that. Maybe you'll use that, maybe not. You won't necessarily know that that's the right thing to do, but usually, so that's not always, but often, usually any factoring or indicated algebra operations should be performed. So these are hints they're giving us to help us with the examples that are coming up. Now, this is so mistyped on the slide, it's even hard to read. So let me see what the hint is. The sum or difference of two trigonometric expressions can be found in the same way as for any other rational expression. And then they have a big mess. Well, they're basically saying that if you have two expressions, you can add or subtract them, whether there's trig functions in them or not. So for rational expressions, rational means a fraction. That means like getting a common denominator or something like that. So let me just provide a simpler example on this same screen to give you the idea that's not as messed up as they're looking at here. So I'm going to ignore all of this because it's just too hard to see what they're talking about. But let's just do something real simple. If I had like 2 over cosine x plus 1 over 5 sine x, or it could be theta, or whatever the argument would be. Well, the sum or difference of these two rational expressions could be combined just as if they didn't have trig functions in them, meaning that you would get a common denominator. And so in this case, to get a common denominator, I would multiply the fraction on the right by cosine x in the top and the bottom, because that's the denominator of the left fraction. And I would multiply the fraction on the left by 5 times sine x in the top and the bottom, because then the denominator for both fractions would be 5 sine x cosine x in the bottom over here, and 5 sine x cosine x in the bottom over there. And then when they have a common denominator, I can then go ahead and carry out the addition. So in the top of the left fraction, 5 times sine x times 2 would be 10 times sine x. And then what's added to that on the right fraction is cosine x. Cosine x times 1 is cosine x. And then all of that is over a common denominator that we got of 5 times sine x times cosine x. So they have something like that here. So that if you have a sum or difference of rational expressions, which means fractions, then you would be able to carry out that addition or subtraction like you would with normal fractions, where you need to get a common denominator before adding or subtracting them. Again, more of past algebra that may show up in these current identities that we're now working with. Another hint. As you select substitutions, again, that's an algebra move, keep in mind the side you are not changing because it represents your goal. Yeah, I think it's kind of hard to understand this hint until you are doing a bunch of problems. But let's look at their example and see if we can make sense, because they do have a specific example here. So for example, to verify this identity, tan squared x plus 1 equals 1 over cosine squared x. So this is an identity because it says this thing is equal to that thing. Find an identity that relates to tan x to cosine x. So it says in order to do that, find something that relates that. And so they're saying, since we have the identity that secant x is equal to 1 over cosine, that's a reciprocal identity. And we have an identity that secant squared x is the same as tan squared x plus 1. That's one of our fundamental identities, the Pythagorean identities. The secant function is the best link between the two sides. So they're saying tan can be related to secant and cosine can be related to secant. So secant relates these two sides together. Not sure how that has to do with their hint. And then they don't even do it. That's kind of weird. So for example, the side on the right could be shown to be equal, since it's 1 over cosine squared, so that's the square of secant, that can be shown to be equal to secant squared x. And then secant squared x by the second identity can be shown to be tan squared x plus 1, and that's exactly what you had on the other side. So you've confirmed that the two sides are equal, and you've therefore verified that identity. In this case, we just modified the right side until we got it to look like the left side. And you could have done it the other way around. We could have started with the left side, changed that to secant squared, changed that to 1 over cosine squared, and then we could have verified that the left side can be made to look just like the right side to verify that identity. I guess that's what they're trying to get at here. Another hint. If an expression contains 1 plus sine x, so this is a very specific hint because this is something that works when you do this regularly. If an expression contains 1 plus sine x, multiplying both numerator and denominator by 1 minus sine x would give you 1 minus sine squared x, which could be replaced with cosine squared x. Similar procedure could be used for 1 minus sine x. 1 plus cosine x and 1 minus cosine x. So what are they trying to say here? Let's see if we can flush this out a little bit. If an expression contains this, so let's say we have something like 1, I'm just going to make this up just to try to illustrate what they're talking about, since they're saying to do this, but they're not explaining why that might be helpful. So let's say we had 1 plus sine x divided by cosine squared x is equal to 1 over 1 minus sine x. And we're supposed to verify. All right, so if we had something like this to verify, well, here we can see that there's an expression that contains the thing they're talking about, because we can see that there. See? So it says if you have an expression like that, one of the things to consider trying is to multiply both the numerator and the denominator by 1 minus sine x. Now, they said an expression contained this, and they never said it had a fraction, but I've set it up the way that they are alluding to here, just so that it makes sense that it works. So they're saying you could multiply the top and the bottom by 1 minus sine x. So what would that look like? I multiplied this fraction by a big fancy 1, where I have 1 minus sine x. And so the reason that they're doing this is because when you multiply 1 minus sine x times 1 plus sine x, that's what in algebra we used to call a conjugate. And there was a formula when you multiply conjugates together that leads to a difference of squares. So all of that is built into this suggestion. So let me show you what that was and remind you, because they're not really helping with that. So from algebra, we may remember that when you multiply a minus b times a plus b, you get a difference of squares, a squared minus b squared. And so what they're saying is that the 1 plus sine x, you would match up with the a plus b. And then to get the difference of squares here, we could multiply by the conjugate. The conjugate is when you have the same two terms and you just change the plus in the middle to a minus, or vice versa. So 1 plus sine x has a conjugate of 1 minus sine x. So you have a 1 plus sine x, you multiply it by 1 minus sine x, then that product gives you 1 squared minus sine squared x, which is what they say you would get here. If you multiply by that, you would get that. So in the problem I have below, by this recommendation saying, okay, I'm set up this pattern at the top where I have a minus b times a plus b. So I get a squared minus b squared. And specifically in this problem, 1 minus sine x times 1 plus sine x is 1 squared, which is 1, minus sine x squared, or we write it as sine squared x. Now I have to do that on the bottom too. So I have 1 minus sine x times cosine x in the bottom. So I multiplied across the top and I got this 1 minus sine squared, and I multiplied across the bottom and I just get 1 minus sine x times cosine squared x on the bottom. So I'm going to try to keep writing here. I'm going to go this way, I guess. So then they're saying, well, then when you get this 1 minus sine squared x, that can be replaced with cosine squared x because of our trig identity, our Pythagorean trig identities in 5.1. Cosine squared x is equal to 1 minus sine squared x. So that means that on the top where I have 1 minus sine squared x, I would now get cosine squared x. On the bottom, I have 1 minus sine x that's multiplied by cosine squared x. And then because I replaced that on the top, I all of a sudden have the option to recognize that I have cosine squared x in the top and the bottom, so I can cancel those, leaving me with a 1 in the top and 1 minus sine x in the bottom, and then we can see that that's what we have on the right side. So using their hint here in this made-up problem that I created, we were able to verify this identity because we took the 1 plus sine x in the top on the left side and recognized, oh, I have this sort of a plus b thing here, so I can multiply it by this a minus b, and then I'll get the conjugate and I'll get a difference of squares pattern, so that 1 minus sine x times 1 plus sine x becomes 1 minus sine squared x. I replaced with cosine squared x, and I was able to then simplify and be left with what's on the right side. So this is an example illustrating the hint that they're trying to describe here. Okay, let's see what's next. A caution. The procedure for verifying identities is not the same as that of solving equations. Yeah, we are not solving for a letter here. We're not isolating x or isolating theta. You're basically trying to confirm that the two sides are the same. And that might mean converting one side with known algebraic properties or trigonometric identities until it actually is the same as the other side so that you know that they're equal. Techniques used in solving equations, such as adding the same term to each side and multiplying each side by the same term, should not be used when working with identities. Well, that's not exactly always true, because as they set up here in the very beginning, sometimes you're working with both sides at the same time. Now, what they are saying is that you don't want to do things like squaring both sides, but you might multiply both sides by the same thing. That will sometimes be done. There are definitely perils to that, but we don't want to do all the same normal things we do when solving an equation. And usually we don't want to do them because they don't help us do the problem. So we'll just have to kind of look at these problems case by case and try to see what they're talking about here. So now they're specifically looking at verifying identities by working with one side. To avoid the temptation to use algebraic properties of equations to verify identities, one strategy is to work with only one side and rewrite it to match the other side. And I've actually already demonstrated this particular approach a couple of times in the examples that we've looked at. So for example, if we just look at the one we were just doing, I worked on the left side until I made it look like the right side. I never actually did anything to the right side here. That just, by working with the left side, I was able to show that it ends up being the same as what we have on the right side, and that's why they're equal. So that's this strategy they're talking about here. And so let's look at an example of that. So here's what we're supposed to verify. Verify the following equation is an identity. Oh, this yellow is not very clear. Let's try that again. Maybe orange. So here's what we're supposed to verify. Cotangent theta plus 1 is equal to cosecant theta times cosine theta plus sine theta. So in this case, they're going to show us how they just work with one side and try to get it to end up like the other side. And on top of that, they're using one of their hints, which was they're recognizing that the right side is more complicated than the left. There's 3 different trig functions there. There's parentheses with some addition and multiplication. Where on the left side, we just have one trig function and the number 1 that's added. So they say work with the right side because it's more complicated. That was one of the hints, to take the more complicated side and try to make it look like the simpler side. So they pull the right side off by itself and say, all right, here's the right side of the equation that was given. And so what do they do with that? Well, then one of the things I'm pointing out here is they converted cosecant theta into 1 over sine theta using the reciprocal identity. That's also one of the hints that they described above, where you could try converting all the functions into just sines and cosines and simplifying from there. So they chose the more complicated side. They converted the function that wasn't a sine or cosine into that. And then after that, we start using algebra. So then they're taking this 1 over sine and distributing the multiplication across the parentheses to both of those terms. And so if you do that, you get cosine theta over sine theta plus sine theta over sine theta. And then each of those can be simplified. Cosine over sine is cotangent, by it's basically the way I said it by definition. And sine divided by sine is, of course, 1. And they ended up with what was originally on the left side of the equation. So they showed the right side could simply be simplified, and then it becomes what's on the left, and that verifies the identity. So this is a good example in which a couple of the hints that they gave us are utilized, and the problem's not too terrible. It just takes a couple of steps, and we're able to do it that way. Questions, comments, discussions about this? Anything here that is confusing I should explain better or elaborate on? All right, well, let's proceed. More of this to do. Example 2. Verify the following identity. A following equation is an identity. So let's just highlight this. This is what they started in the initial problem, because they do get a little lumped together on these slides. So in this case, they're choosing to work with the left side. Now, it doesn't mean you couldn't do this by choosing to work with the right side. But again, I believe they're choosing the left side because it's more complicated. And there's only one trig function, and it's a sine or a cosine on the right side. So on the left side, if we reduce complexity, maybe convert to trig or not to sine and cosine or something, maybe we can do it that way. So they start with the left side and they just say, all right, I'm going to pull the left side and I'm going to try to make it look like the right side. And you might want to remember that while you're working with one side, you want to keep the goal of the other side in mind. So in this case, the right side is the goal. So that as you're working with the left side, you want it to end up looking like what's on the right side. So what did they do? Well, they distributed. How would you know to do that? It's just something that you're able to do, and you're going to be doing some trial and error on quite a few of these problems. You could have also said, maybe I'll start by converting the tangents and the cotangents all into sine and cosine. It's up to you. So when they distributed, tan squared x times 1 is tan squared x. And then they had tan squared x times cotangent squared x. Well, you may recall that cotangent is the reciprocal of tangent. So they rewrote cotangent as the reciprocal of tangent in the next step, because then you can see that when you multiply tan squared x by cotan squared x, since they're reciprocals, you just get 1. So they get a cancellation here, and that's simplified to just down to just being a 1. So that made the whole thing become tan squared x plus 1. Well, tan squared x plus 1 by one of our fundamental theorems is the same as secant squared. So now the left side, they've got all the way down to secant squared. They definitely simplified it way down. But then we have to say, well, I can't get any simpler than that, but it's not what my goal is. So I want to keep working with that to try to get it in terms of a sine squared function. So then we say, all right, well, secant squared converts not to sine, but to cosine by the reciprocal property. So secant squared x would convert to 1 over cosine squared x. And then how do we convert from cosine to sine? Well, then we have one of our Pythagorean theorem identities that cosine squared is 1 minus sine squared. And since that's on the bottom of the fraction, then we have reached our goal. And by working with the left side, we were able to make it convert all the way into what we had on the right side. And that verified the equation identity. So as we look at these, you really want to try to look at how algebra is being used in case you need some algebra refreshers, or you need to remind yourself of these algebra properties and how to use algebra. And you have to see how the hints are being demonstrated, because at some point you have to think, well, what am I going to do? Not all the problems are going to work just like this one did. Every problem is its own problem, but you have to somehow think of some things to do and try. And so these are trying to illustrate that. Let's look at example 3. So it says to verify that this equation is an identity. So this one, honestly, is kind of hard to think of how a student would think to do what they're doing here on their own, how they would think of that on their own. What they're showing is that on the fraction on the left, so they're choosing to sort of recognize how to do this. On the fraction on the left, you have a single fraction with a single denominator and a difference of numerators. Then on the right, you have 2 fractions with the same denominator, and they are subtracted. So they're reminding us from algebra that when you have 2 fractions with a common denominator that are added or subtracted, then you can just add or subtract the numerators and put them over that common denominator. And so in this case, the reason they're doing that is because they're taking the thing on the left and they're breaking a single fraction into 2 fractions. And that's the part where I like, you've never really done that in algebra. Usually in algebra, you have 2 fractions with a common denominator and you make them into 1 fraction. This case, they're taking 1 fraction with a single denominator and a difference in the top and breaking that into 2 fractions. So they started with the left, and they're using this property from algebra kind of in the opposite direction you normally would. If I have tan t minus cosine t over sine cosine, well, that's the same as tan t over sine cosine minus cotan t over sine cosine. And why would they do that? Well, because on the right side, you have a difference of 2 different things. So instead of having a difference in top of one fraction, if they break the fraction on the left into two different things, maybe they can simplify them down to the right. Maybe that's how you would think of that as motivation to try what they're doing here. All right, so then if they do that, well, then they can say, I'm trying to get a secant and a cosecant. Secant is 1 over cosine, cosecant is 1 over sine. So they pull this tangent off of the top of the fraction on the left and on the right. So they can write tangent in terms of sine and cosine, and cotangent also in terms of sine and cosine, but as a reciprocal. And then when they've done that, well, then they could, for example, do some cancellation here and some cancellation here because you're multiplying fractions. So they're then breaking everything in terms of sine and cosine, so simplification will get them where they want to be. And that leaves them with 1 over cosine squared for the left fraction and 1 over sine squared from the right fraction. And then by the reciprocal identities, they end up with what they had on the right side. In this example, number 3. All right, well, you can see we just did 3 examples in a row that after they gave all of their hints, they're basically just doing a bunch of examples for you. And so I can see there's an example 4. Then when they talk about working with both sides, they do an example 5. They do that. And then they do an example 6. And there are 8 more slides, and I'm going through them quickly, and one that even has some words in it, because you can look over these yourself. We don't have time to go through all of these other examples, and they're already done for you. So I'm not even showing you how to do something that you had to think of on your own because the slides show you how to do it. So at this 3rd example that we just discussed, I'm going to stop the slideshow and let's see if we could pull up a homework problem and try to use that as an example. So in the homework problem, it actually says, start with the more complicated side and transform it to look like the other side. Choose the correct transformations and transform the expression at each step. So in the homework problem, they do try to have you go step by step and break it down with you a little bit. And following along with that, they recommend we start with the right side. They have the right side as guidance in the problem. So let's just try to follow along with what they said. They have tan t minus cotan t divided by tan t plus cotan t on the right side. Okay, so they're saying that's the more complicated side, and they're saying we're going to choose to work with that one. And what can we do with that? All right, so what can we do with this? Well, we have some choices based on the hints. We could, for example, try rewriting this in terms of sines and cosines and try to simplify it that way. That's a possibility. We could try on the top where we have tan t minus cotan t, we could try multiplying by the conjugate of that to get things that were squared instead. We did that before with like 1 plus sine t. We could notice, for example, that cotangent t is just the flip of tan t. So maybe if we wrote it in terms of tan t, it'd be easier to simplify. So what you're going to face regularly with these problems is that there's a variety of options that you have to consider and that there may be some trial and error. So since cotan t is just the flip of tangent t, I'm going to try converting the 2 cotangents into tangent and see if we make progress that way. So from what we have here, I'm going to write that this could be tangent of t minus cotangent is 1 over tangent of t. So the cotangent in the top here can be written that way. And so can the one in the bottom. So then I have tangent of t plus 1 over tangent of t. Then what I'm going to do here is I'm going to simplify this complex fraction by multiplying the numerator and the denominator by the same thing, with the design of canceling out the little denominators of the tan t. So I'm going to multiply the top and the bottom by tangent t. Again, this was something done in algebra when you had a complex fraction, which is a big fraction with little fractions in it, to cancel out the little denominators. When I do this, I need to distribute to both of these. And when I do that, I get tan t times tan t is tan squared t minus, and tan t times 1 over tan t is just 1. Similarly, on the bottom, I would get tan squared t plus 1. And so now I've tried something, and what you want to do to keep in mind is remember what you're trying to get. So then I can go back and say, all right, well, what was it I was trying to get? I'm trying to make that right side end up looking like this. And you can compare what you have with what you have at this point with what your goal is. This is the goal now because we began with the right side and we wanted to make it look like the left. Well, we can now see that the numerator of what I have now looks exactly like the numerator that I want. So I don't want to touch that at all. All I want to do is see if the denominator can be made to look like secant squared t. And what we have is tan squared t plus 1. And so we have an identity. They were writing this in blue, so that we have an identity, one of our fundamental identities, that tan squared t plus 1 is equal to secant squared t. So that will allow me to convert the bottom into what I need it to be to match the left side. So using that identity, I would then say this becomes tan squared t minus 1 over secant squared t. And then I have verified because that's what that was my goal. So in this problem, this was number 30 from the homework, and this was my attempt to do that using the hints that they were suggesting. All right, well, let's just hop over so that you can see what that homework problem looked like when they gave it to you. So here's that same problem that I just copied over, and they said here, start with the more complicated side, and they copied the right side down. And then to try to help you in case you just wouldn't necessarily think of what to do with that, they're giving you options here. Choose the correct transformations and transform the expression at each step. So this is the way they're trying to help you through this process. And so you might look at these different options and then say, what would I do here? And I see these different choices here. So I ended up choosing this. Well, I mean, I just did that, and that it is one of the choices they offer. And then from the next step, or they're saying, oh, what are we using? So I think this is the justification. It says the expression at each step, choose the correct transformation. So what allowed me to do this is the fact that cotangent is equal to 1 over tangent. So that I replaced each of these cotangents with 1 over tangent. So I choose that transformation and I give this justification for that, and I check that. And so this is how they're trying to give you a verification problem and helping you work through the steps. So then at this point, what are they doing? This is where we transform this by multiplying by tangent in the top and the bottom. That's what I did, and they're writing it this way. I don't know. I think the way I wrote it is better, but that's the same equivalent to this, where they sort of got the common denominator of each of these. I just cleared the fractions. Algebraically, those are equivalent. So divide out the common factor, combine the numerator and denominator, factor the numerator and denominator, simplify the complex fraction. Interesting. Did they give us a way to simplify the complex fraction? So I guess some of these you have to kind of figure out the way they want it done, which looks like none of these. I'm not sure honestly what they're saying here. Divide out the column, simplify, no, factor the numerator and denominator, combine the numerator and denominator. I guess that's that. Let's find out. Okay, they're saying that because we combined the numerator terms and the denominator terms, they're saying they summarize that as combine, combine in the numerator and denominator. Yeah, that's okay. So then they took an extra step to say then we would get to this, and that's when they multiplied the top and the bottom by tan t. So simplify the complex fraction. And then in the final step, replacing the bottom with the trig identity, which they just have it done for us. And that's because 1 plus tan squared is equal to secant squared.